And this time we'll make sure that it's actually recording. Yeah, okay, good. We have recording. So reaction 2, right, if there weren't any questions. Reaction 2 is the hydroboration-oxidation. Again, it's 2 steps, right? The hydroboration happens in the first step, and then the oxidation happens in the second step. This part is a single-step concerted mechanism. And then this step has lots of steps. So it's the oxidation part of the hydroboration-oxidation that's actually complex. The hydroboration part is, relatively speaking, simple, except that it's concerted, right, which means we have to draw the transition state. The borane THF complex is actually THF attached to boron by its oxygen. We show it as a complex, so there's kind of a, if you think of this as being a bond there's a negative charge on the boron and a positive charge on the oxygen. But that's in equilibrium with BH3. BH3 itself is unstable, so you can't just buy it. So the electrophile is BH3. The unfilled octet, the electron deficient boron. So what's going to happen is the pi bond is going to attack that empty p orbital that's on the boron, and that's going to build up a partial negative charge on the boron, which means that it's going to look a lot like borohydride, right? And it can then donate the hydrogen. So the hydride is going to attack, and again, since the hydride is the negatively charged part, that's the nucleophile. Right? And the boron is the electrophile. It's all going to happen at the same time. We're going to get a 4-membered ring transition state where we're forming a bond to the boron and breaking a bond to the hydrogen and forming a bond to that hydride at the same time, and we're breaking the pi bond. So the transition state looks like this. Got a partial negative charge on the boron and a partial positive charge on the more substituted carbon, and we're forming 2 sigma bonds and breaking the pi bond and breaking the BH bond, right? So 2 bonds breaking, 2 bonds forming, and when the smoke clears from that, we will have ended up adding a hydrogen to one side and a boron to the other side. This one is actually a syn addition. The hydrogen and the boron are on the same side of the double bond. They have to be because they're attached during the transition state, the 4-membered ring intermediate. Right? This is because it's concerted. So that's all there is to the hydroboration step. Just one step, attacking the boron with the pi bond, and the hydride attacking the more substituted carbon, 4-membered ring transition state. And this is page 4. And then we have the oxidation step. And the oxidation step is going to replace the boron with an OH group. So what we have is we have hydroxide ion, and we have hydrogen peroxide. And we know that hydrogen peroxide's oxygen-oxygen bond is relatively weak. And again, we kind of have a step 0. It doesn't involve the boron yet. It just involves an acid-base reaction where hydroxide ion is going to take off the hydrogen peroxide hydrogen because the pKa of that is 12. And the pKa of water is 15, so it's a favorable reaction. Who wants to tell me what the equilibrium constant for that reaction is?
1 times 10 to the third.
1 times 10 to the third. We are 3 orders of magnitude more acidic than the hydrogen peroxide because of the electron withdrawing hydroxyl group that's attached to it. So we say that reaction largely goes to completion. So now we have the nucleophilic oxygen, and that's going to attack boron. Much of the rest of this is actually equilibrium. Because boron doesn't like having an unfilled octet, I'm actually not going to write the hydrogens anymore, just for simplicity, because they're not relevant. It doesn't like having an unfilled octet, but it also doesn't like having a formal negative charge on it because it's not a very electronegative element. So it can't really make up its mind. Right. So step 1 is nucleophilic attack on boron, or step 2 if you decided to make that step 1, by the hydroperoxide anion. And then the key step is step 2. This is an alkyl shift. But it's not an alkyl shift that's driven by having a positive charge like the carbocation rearrangements. It's an alkyl shift that's driven by having a negative charge. The pair of electrons that used to be the boron boron-carbon bond is going to move over to form a carbon-oxygen bond and kick out hydroxide ion. Right? Hydroxide ion is not normally a good leaving group, but you're in base. So we will have replaced that carbon-boron bond with a carbon-oxygen bond, and now the boron is unhappy again, because now it has an unfilled octet again. This occurs with retention of configuration. So wherever the boron was, the oxygen is in the same place, right? Not relevant here because this is not a chiral center, but if this were a chiral center, we would have the same RRS configuration when we're done with that step. So now boron's unhappy because boron has the unfilled octet, but it just generated hydroxide ion. So it can add hydroxide ion. This is another nucleophilic attack, this time of hydroxide ion on boron. And that one is equilibrium again. It's going to generate the tetravalent boron species. And now boron is unhappy again. Boron is never happy because now it has a negative formal charge. And this is equilibrium. The hydroxide could just fall right back off, but this is another oxygen, and that oxygen could fall off. Terrible leaving group, right? Alkoxide ion, not a good leaving group at all. But if you make it a certain promise, and say, you know, I know you're a terrible leaving group, but there's a proton waiting for you if you're willing to leave in this case, you can convince it that it would be okay to leave. And then in the last step, which is an equilibrium, but an equilibrium that lies very much towards product, this boric acid analog will donate its hydrogen and form the corresponding kind of borate salt. There's a slight complexity to this, which is that there are 3 hydrogens on the boron. And that means it can add 3 moles of the alkene. So when we're showing the mechanism, we don't usually show that. But if we're writing the balanced reaction, 3 of these react with 1 BH3 to form a borate, where you've got 3 of these O groups. Oops, put the 3 on the wrong side. Where you've got 3 of these alkoxy groups attached to boron. So if I were to draw that whole thing out, right, we've got boron with 3 oxygens, and each of those oxygens is attached to the same R group. And now you can see why we don't usually, right, this is a trialkyl-borate. But we usually just leave them as OR groups. So if you wanted to show the mechanism properly, you'd have 3 OR groups. Each of those OR groups can now be oxidized off, and the final product of the last step is actually the BO3 3-, which is borate ion. Right. So it's a 3-to-1 stoichiometry. 3 moles of alkene react with 1 mole of boron. So one step, right, for the first, the hydroboration part, but then 6 steps if you count this pre-equilibrium as step 0, right, and then 1 through 5 to get to the actual product alcohol. Right? So a little bit more complicated than the oxymercuration because the oxidation reaction has so many steps. Questions on that? Let's take a break. I'm going to save this. If you have questions,